All right, electrons. I want you to know that electrons are my favorite unit. This is actually really hard to explain, so this is going to take cooperation on both of us. I'm going to do my best here to explain it through video. Sometimes it's best just to watch me in class and listen to a lecture, but here we go. So atoms are arranged by what we call their principal energy levels, and that tells us how far the electrons are away from the center of the nucleus. There are 5 energy levels, and each of them can hold a maximum amount of electrons. Energy level number 1 can hold 2 electrons, energy level number 2 can hold 8 electrons, level 3 can hold 18, 4 can hold 32, and 5 can also hold 32. The Bohr model of the atom by Niels Bohr was thought to be like the electrons kind of stayed in a circular orbit, almost like planets rotating around the sun. And it really did work perfectly with hydrogen, but didn't explain the other elements at all. Even though Bohr was right about there being energy levels, we now know that they don't, electrons anyway, they don't orbit around the nucleus like planets rotate around the sun. They stay in what's called an orbital. An orbital is the probability where you might find an electron in an atom. Each principal energy level has orbitals. We also call them sublevels. And the first energy sublevel has 1 orbital, and the second energy level has 2 orbitals, the third level has 3 orbitals, and the fourth energy level has 4. Now there are only 4 orbitals. Orbitals can be talked about based on their shape or the pathway that the electrons are moving. Think about it as real estate options. So the first one is the s orbital. That's a spherical shape. Each of them can hold 2 electrons, and that's a very, very low energy level. The p orbitals can hold 2 electrons each, and that's 6 total. So there are 3 p orbitals on every energy level, and each of them can hold 2 for a total of 6 electrons. That's a slightly higher energy level than s. Here we can see the first p orbital overlapping it with the second one, and finally a third p orbital. They're all dumbbell shaped, and they're moving in this almost like figure 8 pattern. And you can see like right here, that's 1 p orbital, this is another p orbital, and this is another p orbital, and they work on that x, y, z axis, plane of existence. All right, our third orbital is what we call a d orbital. There are 5 d orbitals, and each of them holds 2 electrons. So that's a total of 10 electrons. It's kind of a funky orbital. Most of the time, it's this clover shape right here, as you can see. So this is a d orbital. There are 5 of them, 1, 2, 3, 4, 5. And the 5th orbital is not clover shaped at all. It has this like P combined with this circular part, but you'll learn more about that in advanced level chemistry. When you put them all together, this is the shape that the d orbital forms. F orbitals are very complicated, very large, but they have almost like a double clover. So if you look right here, is 1, 2, 3, 4, 1, 2, 3, 4. So every F orbital kind of looks like there's 2 clovers on top of each other. And there are how many? 1, 2, 3, 4, 5, 6, 7. There are 7 of them. Each of these orbitals can hold 2 electrons for up to 14 electrons. So orbitals have this hierarchy. You have the s orbital, there's 1 of them, it holds 2 electrons. Then you have the p orbital, there are 3 of those, and they can hold up to 6 electrons. Then you have the d orbital, there are 5 of those, they can hold up to 10 electrons. I'm going to write this on here. And then you have f orbital that can hold up to 14 electrons. So to summarize, we have orbitals that are s, p, d, and f. followed by their shape or their pattern at which the electron is moving, spherical, dumbbell, clover, or like a double clover, and the number of orbitals per energy level. So for S, there's only one orbital per energy level. There's three at the P, and there's 5 orbitals for the D and 7 orbitals for the F. The number of electrons total that they can hold are 2, 6, 10, and 14 respectively. And the first energy level that we start to see these orbitals show up is, of course, we see the S orbital show up on the very first energy level, but it takes till the second energy level before we get to see P, the third energy level before we start to see D show up, and then it's the fourth energy level before we see the F orbital. If I were to lay out all of these orbital patterns and put them in a corresponding box to the periodic table, this is what it would look like. Now we refer to everybody right here as S block. And everybody right here, this is P block. It's like if they've got P orbitals, they reside on P block. And down here we have, you guessed it, F block. And right here we have D block. Electron configurations are written in standard notation. Standard notation is an order series of numbers. These are called quantum numbers that illustrate where we could potentially find an electron if we were looking for them. So the S is, of course, in this diagram here, the sublevels. All right, this right here, which students would normally call an exponent, that's not an exponent, it's the number of electrons in that sublevel. And then the main energy level is notated by the larger number up front. So for 1s2, I'm in the first energy level in an s orbital with 2 electrons. Each of these electron configuration standard notation quantum numbers will tell us where the electron could potentially be found and the patterns or real estate, if you will, where the electrons are traveling. So let's just see what an electron configuration would look like. So let's look at sodium. So how many electrons does sodium, like normal sodium, have total? So sodium's atomic number is 11, so it has 11 electrons, okay? So we're going to put 11 electrons in an electron configuration. So my first energy level is 1s, and it can hold up to 2 electrons. Then my next energy level is going to contain 2s and 2p. The 2s can hold 2 electrons, and the p can hold 6 electrons. So how many electrons is that right now? 1, 6, 7, 8, 9, 10. So I need one more. The next one in line is going to be 3s, and since I have electrons, that just has a 1 right there, notating that the energy level is 3, and there's only 1 electron in that s orbital. So the electron configuration for normal old sodium is 1s2, 2s2, 2p6, 3s1. If I were to count these little numbers right here, that would tell me how many electrons are in there. The highest energy level that sodium has is 3, right? So it has 3 energy levels, and the highest energy level that sodium has that is completely full is 2. So let's build sodium here. Here's the plane, and you got to imagine that the atom is sitting on like a XYZ plane, right? It's 3-dimensional, and here in the center is where our nucleus would be. The axis is represented by 3-dimensional space. For this presentation, the nucleus is going to be at the center of all 3 axes. So I have 1s, it's spherical shape, centered around the nucleus. 1s is filled with 2 electrons. Then I have 2s. 2s is larger, higher energy level, and it also has 2 electrons. the 2 electrons have a higher energy level than the 1s electrons. So the 2s electrons are generally more distant from each other, making the 2s orbital larger, or appear to be larger in the sense of how we humans talk about it. So technically 1s is like in there somewhere with electrons that are, spinning in opposite direction. And then we have 2s, which those 2 electrons are spinning in opposite directions because they're negative, so they repel each other, so they're moving around as far away as they can from each other. So if I just stopped right here, this would be the atom with 4 electrons, also known as beryllium. So once the 2s orbital is full, then we can start to add the p orbitals. So here is a 2p orbital. I'm going to add another 2p orbital. Remember, each of these guys can hold 2 electrons. And all of 2p has 3 p orbitals, each holding 2 electrons. But each orbital gets an electron before we go back and start to pair those electrons. So every 2p orbital is filled with a pair of electrons. Then we get more real estate, we get a higher energy level, we get 3s. 3s can hold 2 electrons. But in our 3s, because we're doing sodium, there will only be 1 electron on that larger energy level in 3s. So the 3s electrons, they have a higher energy level than 1s, 2s, or 2p. So for that, they're generally found like further away from the nucleus than 1s, 2s, or 2p, where the other orbitals with lower energy levels are closer to the nucleus. And you can see here where that real estate resides on closer to the nucleus and the physical space, where 3s, these electrons are around the all of the second energy level, and the first energy level is closest to the nucleus.